Okay, so let's look at the idea of repeated roots and how this differs. So if we were to consider the differential equation y double prime equals, so it doesn't say equals, y double prime minus 10y prime plus 25y equals 0. We know that this characteristic equation would be r squared minus 10r plus 25 equals 0. And factoring that, we would get r minus 5 squared equals 0, which means my roots are r equals 5 and r equals 5.
Shouldn't it be L equals -5?
No. It is 5. Good question, though, because I sometimes mess that up. Okay. Now, the problem is we only get one solution. And what we really need is a second solution for what we call the second degree of freedom, is how they reference this. Degrees of freedom mean how many unique solutions for the differential equation. So like this is a second order, there should be 2. So 2 degrees of freedom for second order. Now, how do we get the second solution? Because we can't write C1 e to the 5t, C2 e to the 5t, because that's the same thing. We don't have anything unique in that situation. So let's consider the example of y double prime equals 0. Without solving, could you come up with 2 solutions to this differential equation? What would be 2 solutions to the differential equation y double prime equals 0? Give me one. 0. Okay, give me one that's not a trivial solution. C some constant.
Or something just as or something times x, but not.
CX plus C2.
Okay. Do you agree that these 2, I just picked one because 1 is a constant. It could be 27. It could be negative 563. It doesn't really matter. Do you agree that these are non-trivial solutions to the differential equation? If I take the second derivative of 1, we get 0. If I take the second derivative of x, we get 0. Now, this could have a C1. This could be any constant. There, it doesn't matter. So, our general solution here looks like this. We would have y equals C1 times 1 plus C2 times t. Now, what would have given us 1 and t would be something along the lines of y equals C1 e to the 0t plus C2 t e to the 0t. Do you agree that that would give us the same thing? Well, we're dealing with a linear, homogeneous, constant coefficient second differential equation. Second order differential equation. My solutions have to be in the form of C1 e to the RT and C2 e to the RT as well. But in order to consider our second degree of freedom, we're going to have to deal with this case right here. This is what's new. We're going to end up multiplying it by an additional variable. So let's look at what happens. Remember, the original equation we said our r was 5 and 5. So we know one of our solutions to this is the e to the 5t. E to the RT. C e to the RT, but that's fine. Let's verify that this, in fact, will be the other solution or will work as a solution te to the 5t. Okay, so let's check this one right here and let's verify that works. We're pretty confident that e to the 5t works. We just did it in our last notes. We feel pretty good about that. So let's verify this one. If y, our solution, is te to the 5t, then y prime will be, we'll have to use the product rule. So derivative of the first is 1 times the second plus the derivative of the second times the first and y double prime, e to the 5t stays, or it would be 5e to the 5t. Let's do good derivative work. Plus, now I need to use the product rule. So derivative of the first would be 5 times e to the 5t, plus the derivative of the second would be 5 times 5 te to the 5t. So we get 10e to the 5t plus 25 te to the 5t is my y double prime. Okay, let's verify that this works. If I substitute this into the equation, 10e to the 5t plus 25te to the 5t is y double prime, minus 10 times y prime, e to the 5t plus 5te to the 5t, plus 25 times te to the 5t, equals 0. So I'm just substituting in for y double prime, y prime, and y. Okay, let's check our math now. This gives me 10e to the 5t plus 25te to the 5t minus 10e to the 5t minus 50te to the 5t plus 25te to the 5t equals 0. 10e to the 5t minus 10e to the 5t, 25 goes away with those two. And we do, in fact, have 0 equals 0. So, in the case where we have repeated roots, not distinct roots, but repeated roots, my general solution is going to be in the form of C1 e to the RT plus C2 t e to the RT. That's going to be my general solution to this problem. So why don't you take a second and try this next example and see what you get. It does say 0.25. That's a fourth. A fourth is a perfect square. We can do it. Happy Monday. You could give up and cry, but that would make me sad for you. Don't do that. My elbow hurts really bad.
It's so peaceful.
All right, hopefully going through this, if we start with our general solution, when you factor, you get r minus 1/2 squared. R is 1/2. So we get C1 e to the 1/2 t plus C2 t e to the 1/2 t. General solution. How do we do? What? 2 equals C1. 2 does end up being C1. Now let's use our initial conditions. So let's start with the easy one because we don't have to take any derivatives. So 2 equals C1 e to the 0 plus C2 times 0 e to the 0, which means C1 equals 2. And I'm actually going to use that before I take my derivative. So my y1, my general solution is 2e to the 1/2 t plus C2 te to the 1/2 t. Now let's take our derivative. So I get 2 times 1/2, which is just 1e to the 1/2 t. Plus, so I've got a product rule in there. So derivative of the first would be c2. Plus derivative of the second would be 1/2 c2t e to the 1/2 t. That's messy.
That's really
Now let's substitute in this y prime of 0 is 1/3. Fun. So we get e to the 0 plus c2 e to the 0 plus, ooh, this is nice, c2 0 e to the 0. We can deal with that. So subtracting 1, so we have 1/3 equals 1 plus c2, which means c2 equals negative 2/3. That got really messy, sorry. So my explicit, my explicit, depending on where you hear this, would be c1, which we said was 2, e to the 1/2 t, plus, oops, that's a minus though, isn't it? Minus 2/3 te to the 1/2 t. And there's my explicit solution. Yeah, Jake, sorry.
So what if like you only considered that C1 for the solution? Because that's also an equally valid solution.
It is an equally valid solution, but it is not as complete as it could be. But you're not wrong.
So if we just considered that, we could still get a valid answer
Yes.
with the initial values.
With the initial value, you could. All right, so tomorrow, here's what I'll tell you. Tomorrow,